find the GCD of 110 and 490 using Euclidean algorithm. So 490 is equal to 4 times 110. So plus 50. So 110 is equal to 2 times 50 plus 10. So 2 times 50 is 100 plus 10 is equal to 110. So we have 50 is equal to 5 times 10. So 5 times 10, 50. So we have here is 0. So the last non-zero remainder is 10. So our GCD is 10. So find the LCD of 110 and 490. So we have already our GCD. So we have here the LCM A D is equal to A times D divided by our GCD A B. Okay. So 490. So our LCM A is 110 and 490, which is equal to 110 times, this is times 490. So divided by our GCD, which is 10. So 110 times 490 is equal to 53,900. So divided by 10, it is equal to 5,390. So therefore, the LCD or the least common multiple of 110 and 490 is 5,390. What is the prime factorization of 147? So 147 is equal to 3 times 49. So which is equal to 3 times 7 squared. So 7 squared is 49. So this is our prime factorization for 147. Find 2 raised to the power of 98 mod 33. So to find the 2 raised to the power of 98 mod 33, we can use the property of modular exponentiation. So we know that the node set of 33, so the node set of 33 is equal to the node set of 3 times 11, which is equal to 3 minus 1 times 11 minus 1, which is equal to 20. So by Euler's quotient theorem, 20 raised to the power of 20 is congruent to 1 mod 33. Then we can write 98 is equal to 20 times 4 plus 18. So therefore, 2 raised to the power of 98 is equal to 2 raised to the power of 20 times 4 plus 18. So which is equal to 2 raised to the power of 20 times raised to the power of 4 times 2 raised to the power of 18, which is congruent to 1 raised to the power of 4 times 2 raised to the power of 18, which is congruent to 2 to the power of 18 mod 33. So now we calculate 2 raised to the power of 18 mod 33. So 2 raised to the power of 1, which is congruent to 2 mod 33. And 2 raised to the power of 2, which is congruent to 4 mod 33. 2 raised to the power of 3, which is congruent to 8 mod 33. And 2 raised to the power of 4 is congruent to 16 mod 33. 2 raised to the power of 5, which is congruent to 32, which is congruent to negative 1 mod 33. 2 to the power of 2 raised to the power of 6, which is congruent to negative 2 mod 33. 2 raised to the power of 7, which is congruent to negative 4 mod 33. And 2 raised to the power of 8, which is congruent to negative 8 mod 33. 2 raised to the power of 9, which is congruent to negative 16 mod 33. 2 raised to the power of 10, which is congruent to negative 32, which is congruent to 1 mod 33. And we have 2 raised to the power of 18, which is congruent to 2 raised to 10 times 2 raised to 8, which is congruent to 1 times 2 raised to the power of 8, which is congruent 2 raised to the power of 8, which is congruent to negative 8, and which is congruent to 25 mod 33. So therefore, 2 raised to the power of 98 is congruent to 25 mod 33. So this is the answer. To find P, 45,375. First, find the prime factorization of 45,375. So 4,375, our prime factorization for this is 5 raised to the power of 3 times 7 times 53. So in Euler's quotient function, Pn counts the positive integers up to n that are relatively prime to n. So if the prime factorization of n is, so prime factorization of n, let's say p1 raised to the power of k1, and p2 raised to the power of k2, and so on. Let's say pr raised to the power of kr. So then the null set of n, so the null set of n is equal to n times 1 minus 1 over p1 times 1 minus 1 over p2. So this would be the formula, no? And 1 minus 1 over pr. So applying this formula to 45,375, so substitute now. So we have the null set of Rn is 4,375, 45,375, which is equal to 45,375. So we just copy this formula. So 1 minus 1 over 5, which is this one, and 1 minus this one, 1 over 7, and last one is this one. So I put it here, 1 minus 1 over 53. So which is equal to 45,375, 4 over 5, 6 over 7, and 52 over 53. So which is equal to 24,192. So therefore RP 45,375 is equal to 24,192. How many primitive roots are there in between 0 to 20 given that 5 is one of the primitive roots of 39? The number of primitive roots modulo n is given by the null set times the null set of n. So where the empty set or the null set is a Euler's quotient function. So first, we find the prime factorization of 39. So 39 is equal to 3 times 13. So the null set of 39 is equal to the null set of 3 times the null set of 13, which is equal to 3 minus 1 times 13 minus 1, which is equal to 24. So the number of primitive roots is the null set of 24. So the null set of 24 is equal to the null set of 2 raised to the power of 3 times 3. So 24 times 1 minus 1 half and 1 minus 1/3, which is equal to 8. So since the primitive roots are between 0 and 20, we need to find which of these 8 primitive roots fall in this range. Since 5 is a primitive root, we can find the other primitive roots by calculating powers of 5 modulo 39. So 5 raised to the power of 1 is equal, or it is congruent to 5 modulo 39. And 5 raised to the power of 2, which is congruent to 25 modulo 39. And 5 raised to the power of 3, which is congruent to 125, minus 3 times 39, which is congruent also 125 minus 117. And this is congruent to 8 modulo 39. And 5 raised to the power of 4 is congruent to 40, which is congruent to 1 modulo 39. So the powers of 5 modulo are 5, 25, 8, and 1. So therefore, there are approximately 4 primitive roots between 0 and 20, which are 5, 25, 8, and 1. Find the quadratic residue and the quadratic non-residues of modulo 9. So the quadratic residues modulo 9 are the quadratic remainders when squaring integers modulo 9. So first, we have 0 raised to the power of 2 is congruent to 0 modulo 9. So 1 raised to the power of 2 is congruent to 1 modulo 9. 2 raised to the power of 2 is congruent to 4 modulo 9. 3 raised to the power of 2 is congruent to 0 modulo 9. 4 raised to the power of 2 is congruent to 16, which is congruent to 7 modulo 9. So 5 raised to the power of 2 is congruent to 25, which is congruent to 7 modulo 9 again. So 6 raised to the power of 2, which is congruent to 36, which is congruent to 0 modulo 9. So raised to the power of 2 is congruent to 49, which is congruent to 4 modulo 9. So 8 raised to the power of 2 is congruent to 64, which is also congruent to what? Modulo 9. So the quadratic residues of modulo 9 are 0, 1, 4, and 7. So the quadratic non-residues are the remaining integers from 0 to 8, which are 2, 3, 5, 6, and 8.